I apologise for the abstract in the proceeding because it was a bit protracted, but what we wanted to do here is talk about some of the work we're doing at Bristol in addressing the challenges of e-motor drives, and particularly the integration with fast switching power devices. So this is a two-part presentation. So I'm going to introduce some of the problems, if you like, and my colleague Nick Simpson is going to explain to you perhaps one solution to it for using different manufacturing techniques. So if you consider the development, if you like, of e-motor drives, we'll be familiar with the drivers, pardon, of cost, size and weight, electromagnetic compatibility, and reliability, stroke serviceability, or fit and forget. All of these kind of would tend to point, perhaps, towards a more closer integration, particularly of the power electronics control with the electrical machine itself, particularly elimination, for example, of connectors, or addressing EMI would seem to point towards a closer integration. So we can think, well, the natural movement is to physically integrate the power converter with the electrical machine, and this is not new technology. It's available now in industrial drives, and clearly automotive suppliers are looking into this. There are certain challenges associated with it, sharing the physical environment, design for EMC, and reliability issues because the power electronics are being exposed to perhaps a higher temperature, a poor environment than we would necessarily do if they were separately packaged. The other area of concern is sensors. Sensors tend to fail. They tend to be prone to electromagnetic interference. And so another perhaps direction of travel, or parallel direction of travel, is a more functional integration. For example, the elimination of rotor sensors. And that involves a design stage where you design the electrical machine so that it can provide a signature on the power cable to enable the inverter to know where it sits, where it is, and so you know its position so you can control it. So again, that's a coupled design problem, but can be done so with certain electrical machine topologies. And then the next stage, and this is really where we're looking at and we'll address today, is a very close level, I'll call it a module coil integration level. And the diagram shown here from Wisconsin University proposed it some years ago, but it's basically simply putting the electronics and controls within the machine itself on the coils, as it were, directly on the coils. And that's benefits in terms of modularity, EMI, containment, simplified thermal management, shared thermal management, and clearly weight packaging, savings, and much reduced cabling and interconnect. So basically the machine will have a DC input and a control input, and it'll provide the torque output as you wish. But clearly there are major challenges associated with this in terms of the high temperature, the poor environment for the power electronics sitting on the windings with the machine housing. Again, the EMI design, the limited opportunity because of space constraints for integration of filters. We can't have nice AC line filters. We have very little space available for the DC link capacitor, for example. So filtering is an element. And the problem with electrical machine is that it's greatly more exposed to nasty switching waveforms from the power electronics, which can implicate on its life. And the final thing clearly is integrating the control, the complexity of control called control hierarchy within the package. So I'm going to touch not on all those topics, I'm going to touch particularly on one area. And we've been looking at this through a study we've been doing on an integrated AC machine. This is a machine, relatively low speed machine, up to 5,000 RPM, which could be part of a mild hybrid type arrangement. But what we wanted to do is try and take this forward in terms of understanding how we can get machines as small as possible by running to very high fundamental frequency. So there is a low speed machine, it's running at greater than 1 kilohertz fundamental frequency, and we do that by maximizing or increasing the size of the poles of the machine design, many coils, many teeth, we want to reduce costs, so it's designed where the magnetic loading, the strength of the magnetic field is low, and we compensate for that by using a very high ampere stream, a very high conductor volume to compensate for that. And this allows us to use, for example, ferrite magnets or a low volume magnet type design. It is a magnet design. It's also, topology could be used for switch reluctance. On-to concentrated type windings, shared cooling through the integrated inverter bus, not shown in the diagram, but the inverter will sit on the tails of the coils and have shared cooling there. Our preference in terms of control design or system topology was to go for balanced three-phase units, primarily because we're familiar with three phases. It gives us a balanced operation. It's a conventional control in terms of PWM algorithms, etc. And it gives us a degree of modularity and fault tolerance. So this machine we can divide into 4 separate three-phase machines, for example, and each could be run independently, or one could run whilst the other is in some sort of faulted mode to give a limp home capability. The topology would also allow, if you were going to a switch reluctance type machine, perhaps individual power and coils. So if we start looking at some of the ways we might implement this, the coils we want to stick as much conductor in, simply put, so you can use preform parallel compacted stranded coils. The power electronics, as I mentioned, will be cooled through the end rings, which will sit on the coil tails. And one of the key elements of here, it shows the concept. We have a prototype in the lab, which we're now testing. So that's a single switching stage shown there on the right, which consists of an integrated DC link capacitance, a gate drive control, and below that is a power semiconductor switch, H-bridge switch, 2-pole switch, with cooling through the DC bus bars. Now, in looking at this, and previous work, we've highlighted a number of, if you like, technical hurdles. One is the manufacture and design of a coil, and I'm going to elaborate that on a bit more. This is primarily what we're going to talk about today. The space envelope for a DC capacitance filter is very small, particularly when you think about the environment. So we can only use certain low energy capacitor technologies to meet the thermal environment and reliability requirements. And this gives us a very big constraint on the amount of filtering. And what has to move forward, you have to think, well, how do I minimize the filter size? And you have to start thinking of perhaps more sophisticated ways of controlling the switching of a device, for example, through interleaving the PWM between motor modules or whatever, to try and reduce the DC ripple characteristics on the capacitor so you can meet that space envelope. And that, in my mind, kind of highlights this, perhaps a slight negative thought when people think about integrated switch reluctance machines. Removing that capacitor minimizing that capacitor filter ripple is far more challenging in a switch reluctance drive. And there are big constraints. The other thing we came across is, on a prototype level, we're stuck with using conventional packaging, even with single die, and we found that we really can't get the best out of the devices because of the packaging constraints of the power device. Not in terms of thermal, actually, because of the stray inductance. So the next stage of development, we're going to have to move to actually putting down our own die on DBC and doing our own bonding, because the length of the interconnect bonds are so high, the inductance of it, we cannot switch the devices as quick as we would like. So for the remainder of the talk, we're going to perhaps focus on one of those aspects, and that's on problems with the coil, because I guess from a more electrical machine bias. This is some work that published at a recent conference, but it gives you an indication. So if you think about a multi-stranded, parallel-stranded coil, this is a natural way of making a coil. You have multiple conductors in hand, you wind them together to form the coil you want. This shows you an example of a machine which had 26 strands in hand. And what is clear from this is that if you look at the individual strand couple currents, and this is because of the variation in inductance of the individual strands as they sit in the slot and their mutual interaction, there's a huge difference not only in the amplitude of the current between the strands, but they're phased. For example, if you look at strand 1 and compare it to strand 26, they're completely out of phase, and in effect, globally, they actually cancel each other out, so that current is wasted. You also note that the individual strands are exposed to different levels of high voltage switching harmonics, PWM. So there can be a very large imbalance across the wire bundle, which clearly can lead to reliability and failure mechanisms. This manifests itself as something phenomenally we'll well be aware of high AC losses. So when you run to a machine in the kilohertz region, you tend to suddenly find that the conductor losses are 3 to 6 times greater than you would on low frequency or DC operation. And another key point of view, because it's so dependent upon how each individual conductor sits in that slot because of the mutual inductance and interactions, but you can make the same coil a number of times and you'll find a very wide variation due to manufacturing issues of how the lay in the slot occurs between individual coils. And this is a sample of coils we made, and you can see the breadth of variation from coils that might have an AC loss of 3 times that at DC to very poor coils where the losses are 9 times that of a DC value. And that clearly provides a certain amount of uncertainty in the design and problematic because that bad coil will burn itself out, whereas perhaps a good coil might do very well. The other issue, as I alluded to, was that the coils are exposed to very high, fast switching edges because they're very integrated closely to the power electronics. And as we move to higher temperature power devices, such as silicon carbide or gallium arsenide type devices, then those edges become faster. They're beneficial in terms of reducing switching losses, but those edges become very much faster. And there's some published work on looking at the breakdown between 2 stranded conductors, 2 parallel conductors placed together. And although the voltage levels, you might say, are far in excess, perhaps, that we talk about in automotive, please note the y-axis, we're talking about lifetime of insulation in a few hours, in minutes, on the y-axis before failure. And what you clearly can see from the trends is that as we increase the frequency of operation, which makes sense, that the number of occasions where perhaps you might get a partial discharge breakdown will increase, so the life reduces. So moving to high fundamental frequencies will reduce loss. But the other key trend, which as you would see, of course, is that as we speed up switching transient, because of a higher level of capacitive currents flowing through the insulation, leading to breakdown, the life greatly reduces, and it's quite dramatic. So fast switching and high frequency operation is not good for coils compared to more conventional. This is a rather complicated curve, it's just perhaps I threw it in here, basically shows you that there's a voltage area where you can, with a particular, this is for a particular insulation system, clearly different insulation systems will have different characteristics, and you might be able to mitigate by putting improved insulation systems in, but there are key areas where partial discharge and insulation failure becomes a major issue. And you might be able to read the scale on the y-axis, but in this particular case, about 600, around about 700 volts above, when you're starting to get into a regime where you can guarantee that there will be some form of partial discharge failure. Once you go higher, and the probability of that greatly increases and the life reduces. So moving to high voltages may not be a great thing for machine windings. And if we think about the aerospace industry, where we're talking about the more electric aircraft, they're talking about 1.5 kV voltages in a partial evacuated environment where partial discharge gets worse. So they're going to have considerable challenges in designing electrical machines and systems that can deal with this aging effect of partial discharge. And inevitably that's going to add complexity, size and weight, I would have thought. To try and then think, well, okay, how can we perhaps improve the design of the coil, the lay of the conductors to mitigate these things? It's well known, for example, that if you better insulate the first entry coil, which coil nearest the inverter, because that's subjected to the biggest dV by dt, and it diminishes, the severity of the slope diminishes as you progress through the coil turns. So we've been developing some quite complicated circuit models and inductor models to try and understand the high frequency behavior of wound components. And that allows us to perhaps look at optimizing conductor placement, if we could find a way to manufacture that to minimize dV by dt effects. Simply put, you might put a bigger gap, a greater layer of insulation around the first turn compared to the others. And that, as shown from that little graph in the middle, you can, by placement, you can do some reduction in reducing the capacitive currents and therefore the risk of failure. The other area we've been looking at is trying to understand the life degradation of coils, particularly when subjected to these nasty dV by dt. So we've been doing some aging characterization, trying to identify signatures of age, changing capacitance, changing tan delta. Also measuring it, can we real-time measure these things through, for example, common mode current measurement, and correlate that to online measurement of impedance. This is ongoing work, and I'm very pleased to say that recently a large EPSRC grant has been approved to take this further. That grant has actually been led by Professor Jai-Bin Wang at Sheffield University, as a partnership between ourselves, Sheffield, and Manchester University. So we're trying to take that forward, and hopefully we'll be able to, as time progresses, give more and more results and trying to understand the implications of these very high dV by dt on the aging of coils in integrated drives. So this moves on now then to perhaps ways we can address the challenges of the manufacture of a coil, and perhaps ways of implementing some of the outcomes of these aging studies, and I'll pass on to Nick.
So the UK Advanced Propulsion Centre and the Aerospace Technology Institute roadmaps are seeking for electrical machines specific outputs of between 9 and 25 kilowatts per kilogram by the year 2035. Now that's in stark contrast to what we can achieve today, which is about 2 to 3 kilowatts per kilogram. So in addition to all of the challenges that Phil has already mentioned, we're also trying to significantly improve our power density of our electrical machine and drives. Now it's unlikely that this can be achieved by a single technology improvement. So we need to look at the whole system. We need to look at the windings, the insulation, soft magnetic and permanent magnetic materials, machine topologies, and also to address integration. Now these two at the bottom, you won't be able to read them, but they're snippets from the ATI and the APC roadmaps. And by around 2027, so in the next decade, they're looking for elimination of conventional winding processes. Now the reason for doing this is that if we can shape our windings, then we can reduce our physical end winding sizes, we can improve our fill factors, and we can address some of the EMI and degradation challenges that Phil has mentioned. And all of that comes together to improve your power density. Now one method of tackling this problem, of eliminating the winding process, is to use additive manufacturing. So metal additive manufacturing processes, such as direct metal laser sintering, can yield greater than 99% dense parts in both copper and aluminium. So you can see here an example of an inductor that we designed at the University of Bristol. So that has a shaped internal winding which reduces losses. And this is another example of an electrical machine winding developed by a German university, which has integrated cooling channels. So some of the biggest benefits of additive manufacturing is the unparalleled geometric freedom that you're given. So you can start to integrate functionality into your windings. So you can add terminals, you can add cooling channels, you can sculpt end windings, and you can start to integrate sensors directly into the windings themselves at hotspot locations. We have relaxed constraints on conductor aspect ratio. So I don't know if anyone here has ever tried to edge wind a winding for a machine before, but believe me, it becomes very challenging when you get above a certain ratio, because you get crowding of the material on the inner radius, and then you get stretching on the outer radius. It also allows us to look at unconventional shaped profile windings. So rather than having the traditional cylindrical or rectangular windings, we can actually change the shape of the profile of the conductor as a function of space around the winding. It allows precise, repeatable conductor placement, which is something that you don't get with mush-wound machines. Now, some of the challenges for the technology is that at the moment we're at a single material stage, so we can only print single materials. So we can't add insulators and things like that. We have limitations on feature sizes. The material properties that you yield are usually in the region of 50 to 75% of what a pure metal would be. We have slight problems with surface finishes, and obviously cost is an issue. Now, our colleagues at manufacturing technologists and also material scientists, they're taking care of this stuff. So in the next few years, I'm very confident that we'll be in a position to start using this more widely. But when we get to that point, we need to know what can these unconventional shape profile windings allow us to do, and how can we benefit from the precision of the winding production that we're given. So take an open slot concentrated wound permanent magnet machine as an example. So it's an attractive topology for electrical machines. It's an attractive topology for automotive and aerospace, simply because you have the permanent magnet, so you have no field winding, so you have relatively high specific outputs. It's concentrated wound, so you can manufacture your coils in isolation and then slot them onto the stator. You have relatively short end windings, so that you have a relatively high power density. Now, one of the main problems with this topology is that because of the open slots, you get a large interaction between the flux from the rotor and the conductors, which gives rise to very high AC losses. So as you can see in this diagram, at the bottom of the diagram you have a very high flux density, which is time varying, which interacts with your conductors, and the time varying flux generates eddy currents, which leads to high AC losses. But the losses aren't distributed across the coil. You get lower losses back in the slot and then higher losses towards the air gap. The induced loss is linked to both frequency and the amplitude of the impinging flux, and it's more severe toward the air gap. Now, often, this phenomena of the external field impinging on the conductors is the dominant loss mechanism in these type of machines. So how do we mitigate it? Very quickly. Let's move on, shall we? So, on the left-hand side, you have a high fill winding, so you've increased your cross-section. You've got very good low-speed performance, but poor high-speed performance because you've got AC losses. On the right-hand side, you've got reasonable low-speed performance and improved AC performance because you don't have the flux interaction. By using additive manufacturing, we can shape the profile of our conductors so that they conform to the flux lines in the air gap, in the slot, and allow us to basically get a better compromise between the two. So we get a higher fill factor, but we don't have the AC loss problems. And this gives us this kind of improvement. So on the right-hand side there, you see the amount of current you can apply to this winding for a 180 degrees C average operating temperature. And compared to the low fill winding and the shaped winding, we have a 20% performance improvement. We have, of course, manufactured these. They're currently undergoing test, but the idea at the moment is that if we can reduce our losses, we can improve our electric loading, and we can ultimately improve the power density of our electrical machines. Some other potential benefits are that if we can control and we can repeatedly place the conductors, then we can control the insulation gaps and the dimensions, and that allows us to profile the capacitance of the winding. The shaped conductors allow us to minimize the electric field, so we can homogenize it, so we can reduce partial discharge and extend our life. By having the preformed windings, we can use inorganic insulations that aren't applicable to wires that have a high level of ductility. So overall, we can improve our insulation aging. And alongside this, we can minimize batch variance. So if you're making 100,000 of these things, you want them all to perform exactly the same. We don't have that at the moment with mush windings and random wound machines. So just some comments. So these are some of the things that we see that we're going to look into in the future. And I guess at the crux of it, if we want more performance out of electrical machines, we're going to have to start doing things that we haven't done before. And we're going to have to start looking at new technologies. And that's why we've started looking at additive manufacturing and some of the benefits that can bring to electrical machines. Thank you very much.